Okay, so we've proceeded now to part one of the fundamental theorem of calculus, which is dealing with accumulation functions. And let's go through these exercises to sort of talk through the idea. So here we're looking at an accumulation function. I know I use the letter A for these. I kind of like A for accumulation function. That feels right. But the accumulation function here is between 0 and x. So imagine x running between 0 and 14 here. Now we can sort of make sense of the situation. G of 0 would just be the integral from 0 to 0. That has no width. G of 2 is just the area of this rectangle. In fact, all the areas, looking at the picture here, are going to be some combination of rectangles or square or triangles, which we can all evaluate geometrically. So what, width of 2, height of 4, I get 8 for G of 2. For G of 4, now we're the integral from 0 to 4, because let's just remember, I'll scroll up here so it's easier to see. G of 4 would be integral from 0 to 4. So G of 4, it's apparently hard for me to get both of those things on there. Yeah. So G of 4 would be the area between 0 and 4, which is this whole region here. So if this 2-unit box had area 8, then this 2-unit box would also have area 8. We're up to 16. And then this is half of a 2-unit box of area 8. So let's see, that would be 8 plus 8 plus 4. Yeah, 20. Anyways, okay, I'm doing too much work here. On what interval is G increasing? G is our accumulation function. And remember, our accumulation functions increase when our function is above the horizontal axis. Because when our function is above the horizontal axis, the more you go to the right, the more positive your signed area becomes. On the other hand, when the function dips below the horizontal axis, the more you go to the right, the more negative signed area you accumulate. And our accumulation function begins to decrease as soon as our function f dips below the horizontal axis. That's harmonizing geometrically. And in fact, we saw the algebra that associated with that. I believe that was the first fundamental theorem of integral calculus. Where would you have a maximum? Well, when the accumulation function goes from increasing to decreasing, the accumulation function would peak. So the biggest your signed area could be would be evaluating at x equals 6. You'd have all the positive area and none of the negative. That's the biggest your accumulation function could evaluate. Sketch a rough graph. Well, we know because G of 0 is 0 based on the expression for our accumulation function, we know our function has to go through the origin, which gives us one of those two. And then beyond that, I just pick another point off of your evaluations and see what happens. Or maybe you could even use this maximum bit, because we know the function hit a maximum at 6. And this is not a maximum at 6. This is a maximum at 6. I like this guy. So there's another way to go about it. You could also, like I said, use the actual data points that you found. It's 6 to one and a half dozen to the other. It really doesn't matter which way you do it. Okay, similar question to the last. Use part one of the fundamental theorem. What do you notice? G prime is the same as f. That is the fundamental theorem, right? Because if G is the accumulation function, if G is an integral, the derivative of an integral is the original function itself. And that's exactly what part C says. Okay, so this is just like the one above. I guess G double prime, we'd have to be evaluating f prime now, right? Because if G prime is f, then G double prime is f prime. So take that one logical step further. This is looking now not, well, whereas G of 3 is the area between 0 and 3, and G prime of 3 is the evaluation, the function height at f of 3. G double prime is the slope at f of 3, which you should be able to deduce from the picture. So that's kind of fun, actually. I don't know if I've ever seen that before. Does G have a local maximum minimum at x equals 6? Well, the area was all above the axis up to 6 and then starts going below. So in fact, G of 6 would be about as big as you could imagine it. And G of 7 is less than G of 6 because now you're including negative area. So G of 6 should be a local maximum. And G of 9 correspondingly would be a local minimum because you were adding in negative signed area on your way to 9. Once you get past 9, now you're throwing in positive signed area. So G of 9 is relatively small compared to G of 10. The function sort of that is the accumulation function bottomed out at 9 if you're looking at the area that's accumulating. Right, this is direct fundamental theorem. If this is our accumulation function, take the derivative. The derivative is exactly the function inside, but in terms of x. Oh, that's a rinse and repeat. This is a precise accumulation function. Oh, okay, so this is the bounds being flip-flopped. So when the bounds are flip-flopped, we change the sign. That is in fact exactly the hint that's been given. So it might be easier to think of f of x as negative integral from 0 to x, because when the x is on top and you take the derivative, the first fundamental theorem applies, and you get exactly the function on the inside with x instead of t. And so yeah, this would just come out to be negative square root 7 plus secant 8x, and that's the story. Right, this is the one that we talked about in class as well towards the end, which is utilizing the chain rule. Just to remind yourself here, and let me just take a moment here to maybe process this a little bit more. So we might think of h of x here, right? Okay, let me grab a pen. We might think of h of x here as, oh, what the hell just happened there? I'm not even sure what that stray mark was. Okay, so we might think of this as an accumulation function evaluated at e of x. And so when we take the derivative, h prime x, sorry, I don't have a touch screen and nor a touchpad or anything such as this, so this is really sloppy. But you just use the chain rule. So this would be a prime of e to the x times e to the x. Why e to the x here? This is the derivative of e to the x. This is using the chain rule. And what is a prime of e to the x? Well, a prime is just the function on the inside. So really this would be just like f of e to the x times e to the x, which f of e to the x is just 2 ln of e to the x. So putting this all together, I get 2 ln e to the x times e to the x. That last times e to the x is from the chain rule. The 2 ln e to the x is taking the derivative of our accumulation function, namely the function on the inside, and evaluating it at e to the x using the chain rule as well. So that's the idea there. Let me close out of that. All continuous functions have antiderivatives. This is the takeaway of the first fundamental theorem. If your function is continuous, then yes, there is a function whose derivative is that function, namely the accumulation function of interest. So all continuous functions have an antiderivative of their accumulation function. So that's not bad. All continuous functions have derivatives. Is that true? No. The absolute value function, right, is the classic example of a continuous function that has a cusp. So yeah, not all continuous functions are differentiable, but all continuous functions are anti-differentiable. So isn't that interesting? It seems like antiderivatives are harder to process in some sense mentally, but that's really only an artifact of us being more familiar with derivatives initially in our study. Ultimately, continuous functions are more well-behaved with respect to anti-differentiation because for every continuous function, their accumulation function is an antiderivative. Yeah, quite a nice thing, but not all continuous functions have derivatives. Take the absolute value function. Its derivative is not defined at the at its vertex point. So, right. Oh, is this subtle? Note, this expression is not the first fundamental theorem. Because in the first fundamental theorem, you're taking the derivative of a function with x at the top. What's written here, the integral from a to b is just a number. So the area from a to b of f of x dx is just a number. Take the derivative of that number, you will get 0. If 0 was on the right-hand side, it would be true. In fact, this would only be true if f of x was the constant function 0, which is not what f necessarily needs to be, which is why this would be false. So if f is just a generic continuous function, well, the integral from a to b of f of x dx is just a number. It's the number associated with the signed area under the function. Take the derivative of that number with respect to x. Yeah, you definitely don't get f of x back unless f of x was equal to 0 to begin with. So, right, hey, that wasn't actually that bad. And that is part 1, I suppose, the first fundamental theorem of integral calculus in WebAssign form.